For these rational functions, now we are going to go ahead and look at their domains. We're going to put that into interval notation, and then we're going to calculate if there are any horizontal asymptotes, vertical asymptotes, and if there are any holes that exist. The first example, in order to find domain, we would like to make sure that we're not dividing by 0, right? We have x in the numerator. Any number is allowed to get plugged in for just x. If we have x squared plus 9, what we might like to do is go ahead and solve that for 0. But quickly you might notice that we're going to run into a little bit of a problem here, as we have x squared equals -9. So when I go ahead and take the square root, which by the way gives me plus and minus, I will get plus and minus 3i out of that. So that's complex. But when we're talking about the domain, we're talking about real numbers, okay? So this is not concerning us. Therefore, we can actually plug in anything into this function from -infinity to infinity. And if we think about that for a second, right? If I plug any number in for x, positive or negative, and square it, it's going to be positive. Then I am adding another positive number to it. So my numerator is always going to be positive. So there's no way for it to become 0 without using a complex number. So the domain here is just -infinity to infinity. The second part of the problem says, can we go ahead and find any horizontal asymptotes? To do that, we need to determine the degree of the numerator and degree of denominator. So we have degree, and I'm just going to do of n is 1. The degree of the denominator d is 2, right? We have x to the first power and we have x squared. That means that we have degree n is less than degree of d, or the denominator. So if we look back up at the top here, the degree of the numerator is less than the degree of denominator, then y equals 0 is our horizontal asymptote. So y equals 0 is our horizontal asymptote, okay? Next, we would like to find if there are any vertical asymptotes. Vertical asymptotes occur when the denominator is equal to 0, right? And it gives us the roots. Well, we've already determined in part A that the roots are all complex. So that means that there are no vertical asymptotes. Okay? The last part says find where the function has holes. Well, a hole occurs at a point where you think you might have a vertical asymptote, but you have the same factor in the numerator and denominator. And in this case, we don't have that, so there are also no holes. So this might not seem like the most interesting case, but let's hop over and look at the picture. All right, so I've already plotted the function and I zoomed in a little bit here so we can actually see the shape. And you'll see that if I zoom out, that it's a little hard to tell, but all right, we have this point or this line here, y equals 0. Now here's the interesting part, right? We just got done saying that it's an asymptote, we can never touch it. But what we mean is specifically that as we go off to infinity, right, this way, we can never touch the line. And as we go off to -infinity, we can never touch the line. But it's okay that it just so happens to cross the line here at 0. So no, that's a little weird, but just keep in mind the definition says as you go off to infinity, right, you can see that this is getting closer and closer to the axis, but it'll never touch. All right, let's go ahead and take a look at another example. We would like to find the domain first. So we really would like to factor this as best we can. So we're looking for two numbers that multiply to -3 and add to -2. That would be x minus 3, x plus 1. So g of x then factored is 3x squared over x minus 3, x plus 1. Again, the numerator doesn't care. I can plug any value of x in there and it's fine. There are no restrictions. In the denominator, however, remember we have to set this to 0 and solve. So we get x equals 3 and we get x equals -1. If that's the case, then it looks like we can go from -infinity to -1, from -1 to 3, and from 3 to infinity. So we can almost be guaranteed that we're going to get either an asymptote at -1 and 3, or at the very least a whole at those points. All right. The second part of the question says, look at the degree of numerator and denominator and tell me if you have any horizontal asymptotes. Well, at the beginning, we had x squared and x squared. So the degree of the numerator was equal to the degree of the denominator. So if that's the case, then what did it say? So let's look back up. It says if the degrees of the numerator and denominator are equal, then the leading coefficient's quotient gives us the horizontal asymptote. So we take the leading coefficient of the numerator, which in this case is 3, and the leading coefficient of the denominator, which is 1, and we get y equals 3. So this is our horizontal asymptote. Okay. Now we want to know where are the verticals. So we've already factored the denominator and solved, and we got x equal 3 and x equal -1. So as long as those factors are not in the numerator, those should be our asymptotes. And we just got done saying that that does not occur in the numerator, therefore this has no holes. All right, let's hop one over to Desmos and take a look. Okay, so I've taken the liberty of plotting the function already. I've also included the asymptotes and I've made them dotted lines. So you can see, right, if I click on these, this is y equals 3. This here is x equal 3. And this is x equal -1. So even though the dotted lines are really defined, if we really zoomed in here, you'll see that we never touch that line on that end or this end. Same thing with this line over here, right? Eventually we'll approach as close as we possibly can get, but we'll never touch. The weird one is this one here, right? The horizontal. Again, remember the definition says as we go off to positive infinity, we never touch the line. Here we just so happen to cross, but that's okay because on this end, as we go to negative infinity, we never touch the line. So those are our vertical and horizontal asymptotes for the function 3x squared over x squared minus 2x minus 3. All right, let's go on to some more examples. For C here, let's look at first the domain of this function. Right, again, the numerator can be any number. We're allowed to plug in 0, negatives, or positive values for x. It's the denominator that restricts us here. So we need to try to factor the denominator. So we have x squared plus 8x plus 15. I need two numbers that multiply to 15 and add to 8. So 15 is 3 times 5, and those just so happen to add up to 8. So that's fantastic. So those are my two factors, 3 and 5. So I get x minus or sorry, x plus 3 and x plus 5. Now, remember we set this to 0, and so each one of these set to 0 is going to give me -3 and -5. So my domain is all real numbers except for -3 and -5. Okay. Now, again, we can expect there to be an asymptote or a hole at those two values. All right, let's continue. Next, we want to know what is the horizontal asymptote. And that's dependent on the degree of the numerator and denominator. The degree here, right, if we look, is degree 2 for both. Remember that if the degrees are the same, right, so if the degree, the numerator is equal to the degree of the denominator, then the line y equals the division of the leading coefficients is the horizontal asymptote. So it looks like y equals -2 is going to be our horizontal asymptote. Okay. What about vertical asymptotes? Well, really, we have to do the whole and the vertical asymptote at the same time. Right? We've already stated that we solved for 0 in the denominator, and we got these two values. So the real question is, what happens if we factor the numerator as well? Well, what's in common there? I see that both of those have a 2 in common. I think I'm going to factor out a -2. So if I take out a -2 out of the numerator, -2 times -9 gives me back 18. -2 times positive x squared gets me back -2x squared. And then our denominator we've already successfully factored as x plus 3, x plus 5. And so I'm going to rewrite this now as x squared minus 9. And you might recognize that as a difference of two perfect squares. And so that's going to factor as x minus 3, x plus 3. Now, you might notice at this point that we have the same factor, x plus 3, in the numerator and the denominator. So because of that, that is going to be a whole. All right. And then the other term, x plus 5, which gave us x equals -5, is going to give us our vertical asymptote. Okay, so this was 2. So x equals -5 is a vertical asymptote. And x equals -3 is a whole. And I just now noticed that as I wrote this up here, I put the -3 first, which is silly, right? Because -3 is closer to 0 than -5. So let me just fix that. So -5 to -3, and then -3 to infinity. All right. So let's hop over to Desmos and take a look. So on Desmos, again, I've gone ahead and put the function in. You'll see that in red here. I've also put in x equals -5, which is the black asymptote. And then the y equals -2, which is our horizontal. That's the blue asymptote that you see there. I did not put in x equaled 3. That was a whole. Now, one problem with graphing utilities is they're not great at plotting holes. But what you can do is I'm going to go in here and I'm going to select my line. And you'll see as I go along, when I get to -3, it says undefined, and you'll see it shows me a hole. But when I go to another point, it's solid, right? So it does do that nicely. Your calculator is not going to do that very nicely. If you go to the table, it'll tell you undefined, but it's not going to put a hole there. We can do this, however. So if I wanted to depict that, I'm going to go ahead and put a point in here. I'm going to let x equal -3. And then I have to figure out approximately what's the function equal to at that point. So if I go here and I scan, looks like as I'm approaching -3, it looks like I'm getting closer and closer to 6. All right, pretty close there. So I'm going to go ahead and plug in 3, 6. Now you'll see it's a solid point. If I hover over here, then I can make this a hole, and it actually is going to detract from the equation or the function that you see there. And if I make it red, then it looks even better. That is a good representation of the function that we just were looking at. So last example here, first we need to know what is the domain. So again, the numerator doesn't care. We need to factor x squared minus x and then set it to 0. So these both have an x in common. Take that out. We get x times x minus 1. The two factors then could separately equal 0. So x could be 0, or x minus 1 could be 0. The first is obvious, just x equals 0. The second, you move the 1 to the right, and you get x equal 1. So this tells me that my domain is all real numbers except for 0 and 1. And we'll determine if those are asymptotes here in just a second. We want to first look at the horizontal asymptotes. And we do this by looking at the degrees of the numerator and denominator. So you'll see that the numerator has degree 3, while the denominator has degree 2. So we haven't had this case yet, so let's go back up to our rules, quite a ways up here. If the numerator's degree is greater than the denominator's degree, there are no horizontal asymptotes. Okay, that makes our life easy. So let's come back here. Because the degree of the numerator is greater than the degree of the denominator, no horizontal asymptotes. Fantastic. Okay, what about vertical? Well, we've already determined points at which this thing can have an asymptote. We did not factor the numerator yet, right? So one thing we have to realize is that x cubed is really x times x times x. And in the denominator, we had x times x minus 1. So technically, right, we have the factor x over x that is repeated in the numerator and denominator. So we should have a hole there, and then we should have a vertical asymptote at x equals 1. So as always, let's plot the function and see what it looks like. Again, I've gone ahead and plotted the function for us. I've included the asymptote here as well. You'll see that it does not cross the line x equal 1. You'll also, if you scan across here to x equals 0, and it's kind of hard to get there, you'll see it says undefined. So if we want to make the plot accurate, we need to include the point 0. It looks like it approaches 0, so we're going to do 0, 0. And then just make that into a hole, and then make it the color of the plot. So this is now an accurate plot. You'll also notice that it looks like there might be a line here that this doesn't cross. So this is a different type of asymptote that we haven't quite gone over just yet.